Yeah, good evening. Yes, can you hear me? Anyone please confirm?
Yes.
Yes, sir.
Okay, okay. Okay, so let's start our discussion. Today we are going to discuss mass transfer. Okay, that is the module 5.1. I'm going to share the screen. Okay, the common instruction is if my voice is not clearly audible and if the screen is not clearly visible. Okay, so please unmute yourself and please inform me immediately so that corrective measure can be taken. Otherwise, difficult to understand whether you are getting proper audio and video quality. Okay, so let's start. So, yes, can you see my screen properly?
Yes, sir.
Okay, fine. Thanks. Okay, so let's start. Okay, so today we are going to discuss module 5.1. Okay, so basically the mass transfer. Okay, so we have to understand what is the mechanism of mass transfer and what are the different modes of mass transfer. As I've already discussed with you, that uh, this mass transfer is analogous to the heat transfer. Okay, so what is responsible for heat transfer? The temperature difference is responsible for the heat transfer. So we can say the temperature difference is the driving potential for the heat transfer. Okay, and what is responsible for flow of current? The potential difference is responsible for flow of current. Okay, so that is the potential difference is the driving potential for the flow of current. Okay, now if we talk about this mass transfer, so what is responsible for mass transfer? The concentration difference is responsible for the mass transfer. That means the concentration difference is the driving potential for the mass transfer. Okay, concentration difference is the driving potential for the mass transfer. Okay, so the this heat transfer is analogous to the flow of current, and this mass transfer is also analogous to the uh, heat transfer. Okay, that's why we study this together, heat and mass transfer. Okay, so fine. Now let's understand what is this mass transfer. Basically, if there is one system, okay, so this system is having one or more components. Okay, and whose concentration varies from one point to another point. Okay, so basically what happens, the transportation of this different species will take place from the region having higher concentration to the region having lower concentration. Okay, so this mass transfer will take place. And what is responsible for this mass transfer? The due to the species concentration difference in this system. Okay, so this mass transfer takes place due to this the concentration difference of this species, that is known as mass transfer, and it will be continued till the concentration difference is there. Okay, so basically the mass fine. So this mass concentration will sorry, this mass transfer will take place till there is the concentration difference is there. Okay, now there are different examples for this mass transfer. Okay, now let's talk about this the various examples. So we can see this mass transfer in this uh, in the refrigeration. Okay, so refrigeration of by the evaporation of this liquid ammonia in the H2 environment. Okay, atmosphere, that we can see in the Electrolux refrigerator. Okay, that is a very uh, okay, the very good example from this industrial point of view. Okay, so the refrigeration by the evaporation of liquid ammonia in the hydrogen atmosphere, that we can see in the Electrolux refrigerator. Now, the humidification of air in the cooling tower, that is also a very good example. Evaporation of this petrol in the carburetor of this IC engine, that is another very good example of this mass transfer. Okay, and this mass transfer we can see in daily to daily life also. Okay, in day to day life we can see this mass transfer example. The dissolution of sugar added to a cup of tea. Okay, that is a very general example that we can see in the day-to-day life. Okay, the transfer of water vapor into the dry air. Okay, drying and evaporation. That is another very general example. Okay, and the separation of the components of a mixture by the distillation or absorption. Okay, that is another very simple or general example that we can observe in day-to-day life. Okay, so what we have concluded on the basis of this mass transfer is basically we can say when the system is not in equilibrium. Okay, so the physical quantities move from the region of higher level to the lower level until the equilibrium is achieved. Okay, so there is the mass transfer that will be caused by the variation in concentration of various constituent species. Okay, so this mass transfer is known as the diffusion, for which the driving potential is the concentration difference. Okay, so the we can say here we'll write the driving potential is concentration difference. Okay, now let's talk about so basically generally we can define the transfer as the basically the mass transfer refers to the diffusion of this chemical species components from the region of higher concentration to that of a lower concentration. Okay, now the modes of mass transfer are, there are three modes of mass transfer. Number one, mass transfer by diffusion. Second one, mass transfer by convection. Third one is a mass transfer by change of phase. Okay, now what is the meaning of this? Let's talk about this one by one. So mass transfer by the diffusion. Okay, just give me a minute. Yes, can you see my screen properly? Anyone please confirm? Hello? Anyone please confirm? Can you hear me properly?
Yes, sir.
Okay, okay, thanks.
Screen is also visible.
Okay, okay, fine. Thanks. Okay. So these are the modes of mass transfer. Okay, number one, mass transfer by diffusion. Second one is mass transfer by convection, and third one is the mass transfer by change of phase. So let's talk about all this one by one. Okay, so this is the first one is this mass transfer by the diffusion. Okay, mass transfer by diffusion. So let's talk about this. So basically, this is known as molecular or the eddy diffusion. Okay, this is also known as molecular or eddy diffusion. So basically, this mass transfer by diffusion occurs due to the concentration gradient of chemical species component in the system through a stagnant field. Okay, so this happens due to the stagnant field. Okay, so I will write here. So mass, the number one. Okay, so we are talking about this mass transfer by diffusion. Okay, so this we have already discussed. This also known as the molecular or the eddy diffusion. So this mass transfer by diffusion, this occurs due to the concentration gradient of the chemical species component in a system through a stagnant field. Okay, so basically this molecular diffusion is the mass transfer on a microscopic level as a result of concentration gradient of one or more constituent or the species in the system. Okay, so what we can conclude? We can say it is the transfer of mass on a microscopic level. Okay, and what is responsible for this? As a result of, okay, as a result of what? As a result of concentration gradient of one or more constituent or the species in the system. Okay, concentration gradient of one or more constituent or species in the system. Fine. Now, this we can say this the diffusion of the mass from a constituent that occurs through a layer of stagnant fluid. Okay, and it may be occur due to this concentration gradient, temperature gradient, or the pressure gradient. Okay, so what we can say, this diffusion of this mass, this occurs from a constituent. This occurs through a layer of, okay, occurs through a layer of stagnant fluid, and what is it? Okay, and it may be occurred due to the, maybe occurred due to this concentration gradient, temperature gradient, and pressure gradient. Now the examples of this molecular diffusion, we can see this in the dissolution of the sugar or the salt in the hot water, and its uniform diffusion throughout. Okay, so although their molecules are much heavier than the water molecules. Okay, so that is the example of molecular diffusion. Evaporation of the water from a pond to increase the humidity of passing this air stream. Okay, the evaporation of the petrol in the engine carburetor. So these are the general examples, okay, of this mass transfer by the diffusion. Okay, uh, the diffusion of the small fraction of the O2, okay, that is oxygen in the air, into seawater and meet the oxygen need of marine animals. Okay, so these are the general examples of this mass transfer by the diffusion. So, okay, now uh, let's talk about this. We have seen this as the molecular or the eddy diffusion. Okay, so we can see when one of the diffusing fluid is in turbulent motion, so the eddy diffusion will take place. Okay. Now, because we know in the turbulent motion, if we generally talk about this turbulent motion, two types of motion are there. One is the laminar motion, another one is the turbulent motion. So, or laminar flow or turbulent flow. So, in the laminar flow, the particle of the fluid will travel in the straight path. Okay, and in the turbulent flow, the particles of the fluid will travel in the zigzag path. Okay, so the eddy formation will take place and the loss of energy will take place. Okay, so basically, when one of the diffusing fluid is in turbulent motion, okay, let's come to this why we added this eddy diffusion. So when one of the diffusing fluid is in turbulent motion, so the eddy diffusion takes place. So due to the turbulence, the rate of diffusion increases, and due to this, there will be increase in the mass transfer. Okay, so the example of this eddy diffusion process is the dissipation of smoke from a smoke stack. It is general example. Okay, dissipation of smoke from a smoke stack. Okay, now let's come to this the second mode of mass transfer, that is the mass transfer by convection. Okay, so what is this mass transfer by convection? So this mass transfer between a surface and a moving fluid, or between two immiscible moving fluids, is referred as the convective mass transfer. Okay, this is a general. We have general. We know as per the definition of the convection. Okay, so how this convection, as I discussed during this heat transfer by the convection. Okay, so here also, okay, so you can say mass transfer by the convection. So what we can comment, the mass transfer between a surface and a moving fluid, or between two immiscible moving fluids, is referred as convective mass transfer. Okay, so this convective mass transfer depends on transport properties of fluid. Okay, so I will write here in the second. Okay, just a minute. So
Sir, sorry to disturb, but I guess there are some people waiting to enter the lecture. If you can allow them.
okay, okay, yes, okay,
Yes,
just a
sir.
minute.
Thank you.
But there is no one in the lobby.
Sir, we got a message saying ki they're waiting. I don't know.
Okay, but in the, I can see the participants, so there is no one waiting in the lobby.
Okay, sir. Then sorry.
Okay, na. If someone will be there in the lobby, so I will again come here and will allow them.
Sir.
How?
Okay, sir.
Okay. However, there is no restriction. Anyone can join the lecture. Okay. They wait for some time and then they can enter the class. But if there is some, if they are they have some issue while joining the class, so I will admit all. Okay.
Okay, sir. Okay.
Okay. Okay. So let's go ahead. The second one is the mass transfer by the convection. Okay. So we'll see. I will write in mass transfer by convection. So we can say this convective mass transfer depends on transport properties of fluid. Okay, so this depends on transport properties of fluid, dynamic characteristic, dynamic characteristic, so dynamic characteristic of flowing fluid. Okay, dynamic characteristic of flowing fluid means whether it is laminar or turbulent. Okay, dynamic characteristic of, complete this, of flowing fluid. Okay, first one is transport property of fluid. Second is dynamic characteristic of flowing fluid. That is whether it is laminar or turbulent. Okay, so the evaporation of the water by the moving air. Okay, in a desert cooler is the best example for this convective mass transfer. Okay, now the third one, that is the mass transfer by the change of phase. Okay, mass transfer by change of phase. So we can say this mass transfer, this occurs whenever a change from one phase to another phase takes place. Okay, so the mass transfer in such a case occurs due to the simultaneous action of this convection and the diffusion. Okay, this happens due to the simultaneous action of this convection and diffusion. So let's write third one, that is mass transfer by change of phase. Okay, so here you can say simultaneous action of this convection and diffusion. Okay, now, what are the examples? The hot flue gases leaving the chimney, the rise by convection and then diffuse into the atmospheric air. You can see this is a general example of this mass transfer by change of phase. Okay, what is the example? The hot flue gases leaving the chimney, so rise by the convection and then diffuse into the atmospheric air. Now, another example, mass transfer from boiling water into air. That is another best example of this mass transfer by change of phase. Okay, so these are the three modes of mass transfer. Okay, mass transfer by diffusion, mass transfer by convection, and mass transfer by change of phase. Okay, now let's talk about some general terms which are very important to understand this mass transfer mechanism. That is the concentration, velocities, and the fluxes. Okay, so let's see the concentration. First of all, we'll discuss this one. So just a minute, someone is there. Bobby, yes, I've admitted. Okay. Okay, so we'll talk about this the concentration. Okay, just a minute. Few terms which are required to understand for understanding this mechanism of this mass transfer. So what are those terms? The concentration, velocities, and fluxes. It is required to understand. 1 minute, please. These are the terms. Okay. Now let's see so concentration, velocities, and the fluxes. Okay. So these terms are important. Okay. So first of all, we will talk about the mass concentration or the mass density. Okay. Mass concentration and the mass density. We'll write here. The mass concentration or mass density. Okay, so the what is this? The mass concentration of the component A within a multi-component mixture is defined as mass of species A per unit volume of the mixture. And okay, so generally denoted by rho A. So this is generally denoted by this rho A. So what is this rho A? Rho A is nothing but, just a minute, I will use some front pen. This rho A is equal to mass of component A per unit volume of mixture divided by volume of mixture. Okay, just a minute. This is mass of component A divided by volume of mixture. Okay, so what is this mass concentration or mass density? The mass of species A per unit volume of the mixture. Okay, so generally denoted by rho A. So rho A is what? Mass of component A. Okay, mass of component A divided by volume of mixture. Okay, so that is known as mass concentration or mass density. Okay, the unit is kg per meter cube. That is the unit. Okay, now the second one is, second factor is the molar concentration. Okay, these terms are required to understand this mass transfer, the mechanism of mass transfer properly. So the molar concentration, okay, so how can we define this molar concentration? The number of moles of the species A per unit volume of the mixture. Okay, it is also known as molar density. It is also known as molar density. Okay, generally denoted by the term Ca. Okay, it is denoted by the term Ca. Okay, so what I've said, let's express this one. What is Ca? Ca is number of moles of component A. Okay, number of moles of component A divided by volume of mixture. Okay, now what is the unit? Unit is kg mole per meter cube. Kg mole per meter cube. That is the unit, okay, of this molar concentration. Okay, now we have to see this, we have to work, we have to see what is Na. Okay, that is the, that is what is Na? Na is the number of moles of the component A. Okay, so we'll talk about this. Okay, 1 minute. Okay, so fine. So we'll talk about this Na, that is the number of moles of component A. So what is this Na? So Na, that is the number of moles of component A. It is equal to mass of component A divided by the molecular weight of A. Okay, so what is this? Na is what? We are talking about this one. Okay, so this is Na. Na is what is this? Ca. Ca is the molar concentration. It is also known as molar density, denoted by Ca. Okay, so this molar concentration is nothing but the ratio of number of moles of component A to the volume of mixture. Okay, its unit is this, kg mole per meter cube. Now, what is this Na? Na is the number of moles of component. So this is nothing but the ratio of mass of component A to the molecular weight of component A. Okay, that is mass of component A divided by molecular weight of component A. Fine. Now, so we can say this is Ca is equal to mass of component A okay, mass of component A. Okay, first of all, let's express this, whatever I have said. This is what? Mass of component A divided by molecular weight of A. Okay. Now, what therefore Ca is what? Ca is the mass of component A divided by the volume of mixture. Okay. Ca we have already expressed. Okay. So mass of so Ca is nothing but the mass of component A divided by the volume of mixture into Ma. Volume of mixture into this Ma, that is molecular weight of A. So mass per unit volume, that is nothing but this, we can take this as the density. So rho A divided by Ma. Okay. Okay. So Ca is the mass of component A divided by volume of mixture into uh, this capital Ma. So this density is what? Density is mass per unit volume. Okay. So mass of component A divided by volume of mixture. So this is rho A. Rho A divided by capital Ma. Okay, where capital Ma is the molecular weight of component A. Okay, now next term is the mass fraction. Okay, so mass fraction. So mass fraction is what? It is the ratio of mass concentration of a species A to the mass density of the mixture. Okay, so generally denoted by XA. So we can write this as XA. Just a minute. Okay, take the this mass fraction. Okay, so this is XA. Okay, so it is equal to, it is what? It is the ratio of mass concentration of a species A to the mass density rho of the mixture. Okay. So it is the ratio of mass concentration of a species A to the mass density rho of the mixture. Okay. So that is the mass fraction. Now let's now the another term. Let's see this. Another one is the mole fraction. Okay. So what is mole fraction? Mole fraction is defined as the ratio of the number of moles of the component A to the total number of moles of the mixture. Okay, so generally denoted by this term. So it is what? It is the ratio of the number of moles of component A C to the total number of moles of the mixture. Okay, so the partial pressure, velocities, and fluxes. Okay, so that is okay. So explanation with this mathematical expression. Okay, so that is required. Okay, so these all these things are required to to be expressed, okay, mathematically. Okay, so let's go ahead. Okay, just okay, so okay, so just we are taking okay, so 1 minute okay, 1 minute break. Okay, so then we'll go ahead. Okay, yes, am I audible? Okay, so let's go ahead. Now we'll talk about this. Okay, so we have talked about this concentration. Okay, so we have studied in the concentration part the mass concentration, also known as mass density, then the molar concentration, that is also known as molar density. Okay, and then we have seen the mass fraction and the mole fraction. Okay, now we'll talk about this. 1 minute, please. Now we'll talk about this velocities. Okay, we'll talk about this velocities. So what is this velocity? The bulk velocity of a mixture. Okay, in which different components, okay, having different mobilities is there. So that we can calculate either, okay, either on mass average or the molar average basis. Okay, so this can be calculated either on this mass average basis or molar average basis. Okay, this can be calculated. Okay, so in a okay, let's take one fluid mixture having two components, component A and component B. Okay, so okay, we have taken a mixture having two components, component A and component B. Okay, so the velocity of A is UA and this velocity of component B is UB. Okay, so basically UA is the mean velocity of component A and UB is the mean velocity of component B. Okay, so we can say this mass average. Okay, the mass average velocity. What is mass average velocity? So mass average velocity is equal to this rho A UA plus rho B into UB. 100, please. Rho A UA plus rho B UB divided by rho A plus rho B. Okay, and this rho A plus rho B is nothing but rho. Okay, the total one. So we can write like this. It is nothing but it is rho A UA plus rho B UB divided by rho. So this is the mass average velocity. Now we'll see the molar one. So the molar average velocity is UACA plus UBCB, okay, divided by this Ca plus Cb. Okay, and if we take for the complete mixture, so this Ca plus Cb is equal to C. You can write like this: US Ca UACA plus UBCB divided by C. Okay. Now this can be written as, okay, so this is what? Ca. Okay, so this can be written as this molar one. This the molar average velocity. This can be written as XA UA plus XB UB. Okay. So we have defined this the mass average velocity or the molar average velocity. Okay, so this mass diffusion velocity of the component is nothing but the velocity of that component relative to the mass average velocity of the mixture. Okay, so we can say this mass diffusion velocity of the component mass diffusion velocity of component A is equal to UA minus U mass. Okay, and this mass diffusion velocity of the component B, it is equal to UB minus U mass. Okay, in the similar fashion, molar diffusion velocity of component A. Okay, because the molar diffusion velocity is the velocity of the component relative to the molar average velocity of the mixture. So, in the similar fashion, we can write this molar diffusion velocity of component A is equal to UA minus U molar, and this molar diffusion velocity of component B. This can be written as UB minus U molar. Okay, so we are talking about this okay, so this term we have discussed. Fine. So okay, so why we have expressed this? Because this mass diffusion velocity of the component is nothing but the velocity of the component relative to the mass average velocity of the mixture. Okay, so we have expressed like this. Okay, and this molar diffusion velocity is nothing but the velocity of the component relative to the molar average velocity of the mixture. Okay, now let's go ahead. So now we'll talk about the fluxes. Okay, fluxes. So the flux, what is responsible for this flux? This is due to the existence of the different velocities and the concentration. Okay, so the different velocities and the concentrations are there. Okay, definitely this fluxes will be there. Okay, so for the species A of a multi-component mixture. Okay, species A for a multi-component mixture, the absolute flux. Okay, so you just pay attention on these terms of absolute flux. So what is the absolute flux? It is rho A UA. Rho A UA. This is the absolute flux. Now the bulk motion flux. Bulk motion flux. What is this? This is rho A into U mass. Now the diffusion flux. Diffusion flux is this. Okay. So what is this MA divided by A? So this is nothing but the mass flow per unit area per unit time. Okay, this is what MA divided by A is what? Mass flow per unit area per unit time. Okay, the absolute flux of any constituent. Okay, so as seen by the observer is nothing but the addition of the diffusion flux and the motion and the bulk motion flux. Okay, what is this? I've said this absolute flux is nothing but the addition of this diffusion flux and the bulk motion flux. So we can say this absolute flux it is equal to diffusion flux plus bulk motion flux. Fine. So from this, let's see, we'll try to find this diffusion flux. So we'll separate this from this diffusion flux. That is mass per unit, mass flow per unit area per unit time. This is nothing but rho A UA minus rho A into U mass. Okay, so take the common. So this is rho A is common. That is UA minus U mass. Okay. In the similar fashion, we can write in terms for the molar basis. Okay. In the similar fashion, we can write for molar basis. Okay. For the molar basis, I can write this as Ma divided by A okay is equal to Ma into UA times U molar. Okay, so what is this Ma divided by A? This is nothing but the diffusion flux. Okay, so you generally write this as the diffusion flux only. Okay, are you getting or not? So what I've said, I've discussed this flux. Okay, so different types of fluxes are there: absolute flux, bulk motion flux, diffusion flux. Okay, so here we have seen this absolute flux is nothing but the addition of diffusion flux and the bulk motion flux. Okay, so we got this equation. So if we want to write this on the molar basis, so we can write this as diffusion flux is equal to this star times UA minus U molar. Okay, so we have studied the different terms. Okay, that is the concentration, velocities, and fluxes. Okay, these terms are required in order to make the analysis, in order to understand the mechanism and of this mass transfer, and we can make the analysis of this mass transfer. Okay, so some related small problems are also there based on this concentration, fluxes, and the velocities. Okay, so these are available in the any book. Okay, so you just the formula based problems are there. Okay, so you just go through these small problems. Okay, so these concepts okay will be more clear, okay, when you will apply this while solving these small problems. Okay, and in case of any difficulty, you please ask those problems based on this concentration, velocities, and fluxes. Okay, now let's talk about the Fick's law. Okay, so Fick's law of diffusion. Okay, the very important law as far as this mass transfer is concerned. Okay, so let's talk about this Fick's law of diffusion. Okay, just a minute. Okay, so let's talk about this Fick's law of diffusion, a very important law as far as this mass transfer is concerned. Fick's law of diffusion. Okay, so what is this Fick's law? So basically, this Fick's law relates the mass flux to the concentration gradient of a species in a mixture. Okay, so let us consider a system with two components A and B. Okay, so let's see. We'll draw this. Okay, so this is okay now. Okay, just a minute. Okay, we'll draw this diagram first and then we'll go ahead. Okay, so what is this? This is species B. Okay, and what is this? This is the species A. Okay, now let's see. So what I've discussed. So okay, so let's draw one more figure. Okay, then the things will be more clear. We will talk about this concentration. We'll talk about this concentration level. Okay, so we'll plot a graph. This is what this is the graph between the concentration. Okay, so this represents this X. Okay, so we have plotted this one. We have plotted this graph. Now we want to show the concentration behavior. Just a minute. And okay, so what is this? This is basically, this represents the concentration of species A, and this represents the concentration of species B. Okay, that is, this represents Ca, concentration of species A, and this represents Cb, that is the concentration of species B. Okay, now let's see. Okay, so I've already told you this Fick's law of diffusion is very, very important for this module. Okay, the mass transfer. Okay, so as far as the mass transfer is concerned, it is most important law, that is Fick's law of diffusion. Now, this what is this Fick's law? So this Fick's law relates the mass flux to the concentration gradient of a species in a mixture. Okay, so we have considered a system with two components, component A and component B. Okay, what we have considered? We have considered a system with two components A and B. Okay, a thin partition is given. Okay, a thin partition which separates the components is removed. Okay, this thin partition. Okay, so a thin partition which separates the components is removed at okay, at an instance. So the two components diffuse through each other until they reach at an equilibrium state, and concentration of the components becomes uniform throughout. Okay, very simple to understand. What we have done, we have taken a thin partition that separates the two species, species A and species B. So we will remove this thin partition. Okay, we'll remove this thin partition. So the two components diffuse through each other until they reach the equilibrium state, and concentration of the component becomes uniform throughout. Okay, so this mass transfer by the diffusion in binary gas mixture. Okay, so basically we can say so this is the diffusion rate is generally governed by the Fick's law of diffusion. So according to this, in a gas mixture, the diffusion mass flux of a constituent per unit area uh, is directly proportional to the concentration gradient. Okay, so what is the statement? We will write the in a gas mixture, the mass flux of a constituent, okay, mass flux of a constituent per unit area, okay, is directly proportional to the concentration gradient. Okay, so we express the constant, so we'll write like this: DAB, okay, del by del x of rho A, okay, del by del x of rho A. In this way, we can write like this. Okay, we'll write like this: D rho A by dx. What is this? It will be denoted by JA. What is this? Again, I will again repeat this. What is this? This is the, according to this, uh, uh, in a gas mixture, the diffusion mass flux. Okay, in a gas mixture, the diffusion mass flux of a constituent per unit area is directly proportional to the concentration gradient. Okay, so we can express like this: Ma divided by A is equal to minus DAB to d rho A by dx. Okay, so where we will write what is the meaning of this, where this rho A indicates mass flow rate, mass flow rate component A. Okay, and the unit is kg per second. Okay, so rho is the mass flow rate of component A, unit is kg per second. A is what? A is the area through which mass Ma is flowing, and the unit is meter square. Okay, now this we can write this Ja, so it is equal to, we can write like this. So it is what? It is the mass flux of component. Okay, mass flux of component A, that is the unit is kg per second meter square. Okay, so here this rho A is the okay, just make one correction here. What is this? This is Ma dot. Okay, whatever I have written here, Ma dot by A. Okay, so this is the Ma. This is Ma dot. Okay, so this is what? This is the mass flow rate of the component A in kg per second. Capital A is the area through which the mass Ma dot is flowing. Okay, so it is in meter square. Okay, so we can write like this. This is Ma per unit area. So that is the mass flux of component A. Unit is kg per second meter square. So what is this rho A? Rho A is the mass concentration. Okay, this is the mass concentration of component A per unit volume. Okay, mass concentration of component A per unit volume. The unit is kg per meter cube. Now this, what is this DAB? That is required to understand. What is this DAB? DAB is the constant of proportionality. Okay, that is also known as diffusion coefficient. Okay, very, very important. Diffusion coefficient. Okay, and it is also known as mass diffusivity of component A in the component B. Okay, or also known as mass diffusivity of component A in component B. The unit is meter square per second. Okay, that is the unit of diffusion coefficient. Now, what is this d rho A by dx? D rho A by dx. So, this represents the concentration gradient of component A, a driving potential for the diffusion of a species. Okay, this is the driving potential for diffusion of a species. Okay, so now here you can see this. Now we have understood this equation. Okay, what is the meaning of each and every symbol? Now you just see what is the significance of this negative sign. So we have to see this negative sign. Okay, so this negative sign. Okay, so please, this negative sign indicates. We'll write the significance of this negative sign. Okay, so the negative sign, this indicates that mass diffusion takes place. Okay, mass diffusion takes place in the direction of decreasing concentration. Okay, I've already we have already discussed all these things in the heat transfer. Here we have seen the heat transfer takes place from the region having higher temperature to the region having lower temperature. Okay, how heat transfer takes place? The heat transfer takes place from the region having higher temperature to the region having lower temperature, and it will be continued till the thermal equilibrium is achieved. Okay, so we say Q is equal to minus K dt by dx. Okay, if the heat transfer takes place by the conduction, so we apply the Fourier's law of heat conduction. So we write the equation as Q is equal to minus K dt by dx. So where this negative sign indicates that the heat transfer takes place in the direction of decreasing temperature. So in a similar fashion, here also we are talking about the mass transfer. So here the significance of negative sign is mass diffusion takes place in the direction of decreasing concentration. So for the component B, we will write the diffusion rate of component B. Okay. We will write the diffusion rate of component B in the component A. So this will be given as okay, diffusion rate of component B in component A, that is given by, in the similar fashion we can write like this. Okay, for the component B. Okay, now it will be minus dBA into d rho B by dx. So we have written this. Okay. Now let us write this as, this is equation 2. Okay, the earlier one, this is the equation 1. Give this as the equation 1. Fine. This is equation 1. So equation 1, equation 2. Now let's see. Now the diffusion coefficient. We'll talk about this. Okay, the diffusion coefficients. So the diffusion coefficient, this DAB and DBA. Okay, the diffusion coefficient DAB and DBA are the relative diffusivities and they are equal in magnitude. Remember this. Okay, so this diffusion coefficient DAB and DBA are the relative diffusivities and they are equal in magnitude. Okay, so basically this Fick's law in terms of this diffusional molar flux Ja, the molar concentration Ca and the mass diffusivity DAB can be expressed in the mathematical expression. So how can we write like this? So we'll write. Okay, so this is I can write like this. Okay, DAB dCA by dx. Okay, so what we have done here, the Fick's law in terms of diffusional molar flux Ja. Okay, the molar concentration Ca and the mass diffusivity DAB. So this we can express mathematically in this way. Okay, so this so what we can say, this for this Fick's law of diffusion is analogous to this Fick's law of diffusion is analogous to Fourier's law of heat conduction and the Newton's law of viscosity. Okay, so this is Fick's law. Okay, that is analogous to okay, so first one is the Fourier's law of heat conduction. Okay, Fourier's law of heat conduction. Okay, Fourier's law of heat conduction, and the second one is Newton's law of viscosity. Newton's law of viscosity. Okay, so Fourier's law of heat conduction is what? How can I express this? Uh, heat transfer per unit area, that is nothing but heat flux. It is equal to minus K dt by dx. Okay, and if I want to express this Newton's law of viscosity, so it is tau is equal to minus mu du by dy. Okay, that we have already studied in fluid mechanics. Okay, so we can say this Fourier's law describes the transport of this heat energy due to the temperature gradient, while this Newton's law of viscosity describes the transport of this momentum due to the velocity gradient. And this Fick's law describes the mass transport due to concentration gradient. You remember this? What is this? Fick's law is analogous to Fourier's law of heat conduction. Okay, and the Newton's law of viscosity. Okay, this is how we can express this Fourier's law of heat conduction, and this is how we can express the Newton's law of viscosity. So this Fourier's law of heat conduction, this describes the transport of heat energy due to temperature gradient. Okay, write this. Transport of heat energy due to temperature gradient. Okay, now what does this indicate? Newton's law of viscosity. This represents transport of momentum due to velocity gradient. And this Fick's law, this represents mass transport due to concentration gradient. Okay, now let's talk about the unit of this diffusion coefficient. Okay, unit. Okay, unit of what? Unit of this diffusion coefficient. Let's talk about this. So this DAB, it is equal to, we can write like this, per unit area divided by d rho a by dx. From this mathematical expression, we can write DAB like this. DAB, okay, this is the equation. So from this DAB is this, ma divided by a divided by d rho a by dx. Okay, we can write like this. So this is what the unit of this is, kg per second meter square divided by, okay, so this is the kg per meter cube is the unit of this rho a, and here dx is there, so meter is already there, so meter cube into meter, it is meter to the power 4. So this kg and kg will cancel out. The meter to the power 4 meter square. Okay, so this will cancel out. So it will, we will get the unit as meter square per second. So this is the unit. Okay, so this indicates the unit of this thermal diffusivity. Okay, and okay, so and the momentum diffusivity. Okay, so this which indicates the unit of this thermal diffusivity and the momentum diffusivity. Fine. Now, we'll talk about this, the physical mechanism of this mass diffusion. This we can understand. Okay, let's see. We have to understand this the physical mechanism. So for this physical mechanism, we'll draw this diffusion. We have to show the diffusion dependence on this concentration profile. We'll draw this diagram. Okay, so this is what this represents. Per unit area, so that is DAB into rho A by dx. Okay, now what is this? This represents imaginary plane. And what is this? This represents the concentration profile. This represents the concentration profile. Okay, so we are talking about the physical mechanism. Of mass diffusion. Okay, so this we can understand with the help of this figure. Okay, basically this shows the diffusion dependence on the this figure shows the diffusion dependence on concentration profile. Okay, so you can see the concentration of the component A is greater on the left of the imaginary plane. Okay, you can see here the concentration of the component A is greater on the left of this imaginary plane than on the right side. Okay, so the higher concentration means more molecules per unit volume. Okay, what is the meaning of this higher concentration? Higher concentration means more molecules per unit volume. So we can say more molecules moving across the imaginary plane from left to right. Okay, so due to this, the net mass transfer from the region of higher concentration takes place to the lower concentration. Fine. So due to this, net mass transfer takes place from the region of higher concentration to the region of lower concentration. So on the basis of this, we can comment that the Fick's law is based on experimental evidence. Okay, so we cannot derive it from the first principle. Okay, so basically we can say it is valid in any state of all matters. Okay, so some conclusions are there on the basis of this. Okay, so let's see what is this. What is this? Uh, what are the comments on the basis of this study? So we can say this Fick's law is okay. This Fick's law is based on this experimental evidence. Okay, so can't derived from first principle. Okay, now next we can say it is valid in any state of all the matters. Valid in any state of all matters. Okay, next is the mass diffusion rate depends on concentration gradient. Okay, let's write this. Mass diffusion. Okay, so this mass diffusion this depends on concentration gradient. Okay. And this concentration gradient is uh, caused by the temperature gradient, a pressure gradient, or some external force. Pressure gradient or some external force. Okay, so what we have concluded here, this mass diffusion, okay, so this depends on this concentration gradient, and this concentration gradient will be caused either by this temperature gradient or pressure gradient or some external force. Okay, now let's go ahead. So you can say the component in the mixture diffuses in the direction of decreasing concentration. Okay, very simple. The component in the mixture diffuses component in a mixture diffuses in the direction of decreasing concentration. In the direction of decreasing concentration. Now the next is diffusion coefficient DAB. Okay, so this depends on temperature, pressure, and the nature of the system components. Okay, so this depends on temperature, pressure, and nature of system components, and nature of system components. Okay, so we can say when the small concentration is there for the of the species A is moving through a large concentration of species B. Okay, we have taken one example. Okay, so just give me a minute. Okay, so okay, so we can say when a small concentration of species A is moving through a large concentration of species B, like air, then the diffusional flux. Okay, this J can be approximated as Na, and this diffusional molar flux Ja as capital Na. Okay, so we'll see this. Fine. So this diffusional flux Ja, this can be approximated as small Na, and the diffusional molar flux capital J as capital Na. What is this? Oh, which is the situation when a small concentration of species A is moving through a large concentration of species B, like air. Okay. Now, so when we work with this Fick's law, so we can say the mass flux Na, or the mass concentration rho A, as in okay. So this the equation one that we have written earlier in equation 1. This one. This is the equation 1. Okay. So when we work with this Fick's law, so we can say this mass flux Na and this mass concentration rho A is in equation 1. So this Fick's law can be expressed in terms of molar concentration Ca and molar flux capital Na. Okay. And for the gases, the Fick's law can be used in terms of partial pressure by using the perfect gas equation of the state. Okay. So what is um, the perfect gas equation in a state? That will write. So that is the equation is P is equal to rho RT. P is equal to rho RT. Okay, so this is the equation. Okay, so basically for the gases Fick's law um, may also be used in terms of partial pressure by using the perfect gas equation of a state. So this is the equation P is equal to rho RT, where rho is where R is the specific constant, specific constant in terms of universal gas constant. Okay, in terms of universal gas constant, this Ru is equal to this Mr. Okay, for a gas component A. Okay, for gas component A. Fine. So this rho A can be written as Pa by RT, and that is nothing but Ma Ca by R. Okay, so this Ru into T. This we can write. Okay. So the the density rho A. Okay, this density rho A. This represents the mass concentration of species A. So then the Fick's law will be Ma by A is equal to minus DAB into Ma divided by RUT into dPA by dx. In this way we can express. Okay, now this is let's assume this as this is the equation 4A. Okay, now we'll see for the gas component B. Okay, for gas component B. Okay, that is an isothermal diffusion. Okay, if the gas component B is an isothermal diffusion, so we can say this Mb divided by 8 is equal to minus dBA into Mb divided by RUT into d rho b by dx. This is equation 4b. Okay. Now we'll talk about this diffusion mass diffusion coefficient. So that is the last topic, okay, of today's lecture. So now after this we will stop. Okay, so mass diffusion. Okay, this is the last thing we are discussing in this Fick's law of diffusion. So mass diffusion coefficient. So this is this mass diffusion coefficient is nothing but the constant of proportionality. Okay, that is denoted by this symbol DAB in this Fick's law. So that is also known as mass diffusion coefficient. Okay, or the mass diffusivity. Okay, this is also known as mass diffusivity. Okay, so this mass diffusion coefficient is also known as the mass diffusivity, generally denoted by DAB. Okay, in the Fick's law. So this its value varies from okay, this value, the value of this mass diffusion coefficient varies widely from phase to phase. Okay, so due to the complex nature of this mass diffusion, this diffusion coefficient is usually obtained experimentally. Okay. Uh, okay, so what is the conclusion of this mass diffusion coefficient on the basis of overall study? We can say, due to the complex nature of this mass diffusion, the diffusion coefficient are usually expressed experimentally. Okay, the kinetic theory of gases, okay, the intends that the diffusion coefficient for the binary gas at ordinary pressure is basically independent of mixture composition and increase with temperature while decrease with pressure. Okay, so what is the relation? How can we say this? We can say this diffusion coefficient, this is directly proportional to T to the power 3 by 2 and inversely proportional to P. Okay, so what we are saying, for this the binary gases at ordinary pressure is basically independent. Uh, okay, we have applied this kinetic theory of gases. Okay, so this kinetic theory of gases intends that the diffusion coefficient for the binary gas at ordinary pressure is basically independent of mixture composition, and it increases with the temperature and decreases with the pressure, that we can say. As the temperature increases, this diffusion coefficient will increase, and as the pressure increases, the diffusion coefficient will decrease. So this binary diffusion coefficient, okay, at a specified temperature and pressure, okay, that can be determined by the equation. So what is this equation? We will write this equation. This DAB is equal to 435.7 T to the power 3 by 2 pressure VA to the power 1 by 3 plus VB to the power 1 by 3, okay, into square root of 1 upon capital MA plus capital MB. So this is the equation. Okay, this is fifth equation. Okay, so let's see what is the meaning of each and every symbol. So we'll see where this DAB is what? DAB is the diffusion coefficient. This is the diffusion coefficient. The unit is centimeter square per second. T is the absolute temperature. If I'm saying absolute temperature, that means the value is in Kelvin. What is this P? P is the total pressure of the system. Total pressure of the system. The unit is Newton per meter square, or generally either in Newton per meter square or Pascal. Okay, what is this VA? This VA represents this molecular volume of component A, and VB represents this molecular volume of component B. Now, what is MA and MB in this expression? Okay, we have seen T, meaning of T, the P, VA and VB. Now, let's see what about this MA and MB. So, this MA represents molecular weight of component A, and MB is the molecular weight of component B. Okay, so we have seen what is the meaning of each and every uh, term in this expression. Okay, so this is the expression. Okay, now let's see. DAB is directly proportional to T to the power 3 by 2 and inversely proportional to P. So on the basis of this, okay, we can write like this: the diffusion coefficient for the gases at different temperature and pressure. So this can be related as T1 by D2. It is equal to T1 by T2 to the power 3 by 2. And since it is inversely proportional to P, so it will be equal to P2 by P1. Okay, so this expression we got. So this is sixth equation. Okay, so for the diffusion coefficient, two important observation we can see. So what are those observations? We'll write those observations. The first is the diffusion coefficient is highest in the gases. Okay, this is highest in gases and lowest in solids. Okay, and the second is diffusion coefficient diffusion coefficient this increases with temperature and decreases with pressure. Increases with temperature and decreases with pressure. Okay, so these are the two comments. These are the two observations based on the overall study. Diffusion coefficient is highest in the gases and lowest in solids. And this diffusion coefficient uh, increases with temperature and decreases with pressure. Okay, so after this, we have to study the general mass diffusion equation. Okay, so today we'll stop here, and in the next lecture on the Thursday, we will cover the remaining portion of this module 5.1. Okay, so we will study the remaining portion of this module 5.1 in the on Thursdays, our regular lecture on Thursday. Okay, I will stop here.
Thank you, sir.
Uh, Thanks.